Start in a second. Okay, so let's start with the disclaimer. You will see not this floor, the floor upstairs, a very nice coffee break, very well organized, is not our. Our coffee break is not nice, is not well organized. Okay, let's go. David Weiss, Penn State, Hydrodynamization and local prethermalization.
That was an excellent job of saying hydrodynamization. You've never said it before out loud. So I'm going to be talking about experiments at Penn State. The people who've done most of the work here are the ones in light blue, Yuan Le, Neil Mavania, and Josh Wilson. New students on that experiment are Kush Dave and Emma Hogan. Our theory collaborators are listed here. One of them is in the audience, and the other ones are there. And that's just the rest of my current group. So what I'm going to do in this talk is I'm going to give some background on integrable systems, particularly with regard to 1D gases. And I'll introduce the concept of a nearly integrable system and how that is useful. In the lab, we don't really have integrable systems, but we have things that are in a meaningful way nearly integrable. And when you have these systems, you can study their dynamics. The dynamics have typically good separations of timescales, and you can often calculate pretty reliably the dynamics that you see. And what the whole thing is sort of leading towards is the case that I'll make by the end, which is that even though there's something about integral systems, sort of a special point, nearly integral systems includes quite a lot of things, including experiments that can be actually executed in the lab. But you can actually use the insights that you get from these studying nearly integrable systems to understand the dynamics of totally non-integrable systems in a way, with a clarity which is sort of surprising. And you'll see that by the end of the talk. So I'll start off with background physics about 1D gases, the Liebel model integrability, and the concept of rapidities. And then I'll explain how we measure momentum distributions in the lab and rapidity distributions in the lab. And then I'll talk about two ways to do quenches on those experiments. One is trap quenches, where we validate the theory of generalized hydrodynamics. And then I'll talk about wave function quenches, which is where we can do all the things that I said we're going to do on the last slide. So after a wave function quench, we have hydrodynamization and then local prethermalization. There are a few timescales, and I'll explain all of those. So just as a warm up and what's happening in a 1D gas, if you have a non-interacting two-particle interaction, then a bosonic wave function, two-body wave function would look like this, and a two-body fermionic wave function would look like this. It's anti-symmetric about the origin, symmetric about the origin. And then if you add infinite repulsive interactions, then the wave function of bosons would be like this. That's a time-shared O gas, and which is to say it's still symmetric, but the probability of the particles being overlapped with each other is zero because it costs too much energy. And then if you take the fermions and just apply the signum function, so change the sign of one size, you see that looks like a time-shared O gas. So there's a mapping between a time-shared O gas, infinitely coupled bosons, and non-interacting fermions. So you see the actual wave function of non-interacting fermions is this, for pairwise, and for the strongly interacting bosons is this. So they're not exactly the same, but they're the same for everything which depends upon the wave function squared. So local pair correlation, spatial distributions, energy is all the same between those two, between the Fermi gas, non-interacting Fermi gas, and the time-shared O gas. But since you see the wiggles in the wave function are different in these cases, things that are non-local, like momentum distributions, they're not fermionized. The momentum distribution of a strongly interacting Bose gas is significantly different from that of a non-interacting Fermi gas. Okay, so with that as background, I'll talk about the Liebel model. Liebel model is pretty simple. There's a kinetic energy term. It's one-dimensional. There's a kinetic energy term per particle, and there's a pairwise delta function interaction for every pair of particles. And you can solve that exactly with solutions that are parameterized by this parameter gamma, which just depends upon constants that are in this thing. You see, it depends on what the strength of that interaction is, and it depends on the 1D density. It's an integrable system, which is why you can get these exact solutions. And it also means that there's extra constants of motion. I mean, if you're sort of an infinite set of extra constants of motion, but those constants of motions are called the rapidities. It was shown in 1998, just a few years before the experiments came online, that if you have a real 3D gas confined in a waveguide, you can get a good approximation of the Lieb-Liniger model for that gas. So to understand what the solution is of Lieb-Liniger gas in the various regions, you can consider gamma much greater than 1. That's the Tangshan gas. That's where kinetic energy dominates because it costs too much energy for two particles to be in the same place. Happens at low density or large G1D. That's where you get this Fermionized spatial and rapidity distributions. And then in the other limit of weak coupling, then the mean field energy dominates. And that happens at high density, where it's not as costly to have particles overlapping. So a lot of equilibrium properties of these gases have been measured in my lab and many other labs. And in all those experiments, you have to put the particles in a trap. When you put the particles in a trap, it lifts the integrability. And the way the theoretically approach the solution is just using a local density approximation to look at the Lieb-Liniger gas locally, given for whatever the density is at some point in the trap. So the first thing is that the reason we can do these measurements in an actual non-integrable gas is because the trap lifts the integrability only in a very weak way. Slight lifting of integrability. So to understand what that slight lifting is, what I mean by nearly integrable, it's helpful to talk about another way to define integrability, which is the absence of three-body diffractive collisions or higher order diffraction collisions. The point is, if you have three particles and they come in and they collide, they leave with the same set of momentum that they came in. And so a system is nearly integrable. So it's integrable if that's the only thing that happens. It's nearly integrable if the diffractive processes, where you leave with a different set of momentum coming out, happens rarely. So that rate is small compared to any other dynamical rates. And then you're nearly integrable. And you can see sort of why this barely changes anything, because you just imagine any sort of three-body collision happening at some point in the trap. Where that collision is happening, it doesn't really know about the trap to any significant degree, so it barely lifts the integrability. And that's the reason, for instance, that this Newton's cradle experiment, where you take a system in 1D gas out of equilibrium and you look at it over a long time, you see for a very long time, there's no thermalization. You get a steady state distribution, which is not the maximum entropy state, and it's because there's all these extra conserved quantities. Okay, so I'm going to turn to the rapidities, because that's what we'll be mostly talking about describing these 1D gases. You can have two definitions of rapidities. One is it's a set of conserved quantities in an integrable system, and the other is that it's the momentum distribution of quasiparticles that arise because of these interactions, right? Where it's a string where each quasiparticle consists of all the particles, and then you put them together. It's what arises out of the solution to the Lieb-Liniger equations. So I had a picture of what the spatial distribution of cartoon picture with the spatial distribution of wave functions in various limits look like. If you look at the rapidity distributions, they all look pretty much the same, whatever the coupling strength is, which is to say they look pretty fermionic. It's like you have a bunch of quasi-particles, and this is in rapidity space, and they each occupy some range of rapidity space. So in the hardcore limit, it looks just like fermions. These are equally spaced rapidity distributions. It's actually also equally spaced rapidity distributions in the mean field limit. And intermediately, it still looks qualitatively like this Fermi gas. It's just that the energy spacing is generally a little different.
Dave?
Yeah.
Should I think of these vertical lines in rapidity distribution as notches?
No, it's not, it's more just a way to separate them out. I mean, the thing is, if you try to, you can put it in a gas and just imagine, adding up a bunch of modes. I would not think too hard about that. There's nothing like notches. It's more like you would, in some region, you'd be filling up a Fermi sea where there's you have the lowest lowest rapidity state and the next highest and the next highest, and this would be, you progressively have higher and higher, different rapidity things.
Rapidity corresponds to like a band.
Yeah, so it's like a band because it's not totally sharp. There's a fuzziness to it. So this is just illustrating both the fuzziness and the fact that they are discrete, separated from each other. Okay, so in a homogeneous trap, then these two definitions are the same thing, right? Because the quasi-particles are the conserved quantities because they're unchanged if you don't have a trap. But if you put it in a trap, then the quasi-particle momentum are not conserved, right? So in fact, there's only really something like a set of rapidities which are not the same as this if you're in the hardcore limit. But in general, it's not an interval system. It's a nearly interval system in a trap. But it is useful to use this second definition of rapidities when you're trying to understand the dynamics of these 1D gases in traps. Okay, so they're not conserved, but they are still the momentum of the quasi-particles. And those quasi-particles, if you're nearly integrable, don't decay. If there's no three-body collisions, then they don't decay. And so they're extremely long-lived quasi-particles. And the fact of that allows you to, you can take advantage of the fact that you're nearly integrable to incorporate those conserved quantities, conserved in the sense that the particles aren't going to change their rapidities just because the interactions of particles with each other. It's a trap would have to be involved. That underscores generalized hydrodynamics, which I'll get to a little bit later. But first, I want to talk about the experiment. So, and for the first thing to think about the experiment is that if you're in a trap, in a 1D trap, and you have non-interacting fermions, then the momentum distribution of rapidities are the same thing. If you have a Tonchero gas, the momentum distribution is heavily peaked up. They are bosons in the end. But if you look at the rapidity distribution, it's just like the non-interacting Fermi gas. And the thing which is pretty clear when you think about it, I just want to be explicit about it, is that if you suddenly turn off a trap, it doesn't change the momentum distribution. It doesn't change the rapidity distribution. That is, you have whatever you had when you turn off the trap is what happens right before you turn off the trap. It's what happens right after the trap. Okay, so you can sort of use that fact to imagine what happens if you take initially trapped bosons and then turn the trap off and leave them in a flat potential. What's going to happen is the particles are going to expand in that one dimension, and eventually expand so that the only significant energy of the problem is the kinetic energies the particles have as they're moving away from each other. Now, that asymptotic momentum distribution that they have in the end is the same as the rapidity distribution at the beginning, because the rapidity distribution through that whole process is conserved. So if you start off with the momentum distribution in a trap, which should look like this, and let it go in the trap, this is for a Tonchero gas, then it evolves over time. The momentum distribution evolves over time until it ends up asymptoting as what the rapidity distribution was at the beginning. And so that's called dynamical fermionization for a Tonchero gas. But if you do that measurement at any gamma, it's not generally fermionizing, but it is giving you what the initial rapidity distribution was. So if you release in a trap and let the atoms expand, pushing off on each other, the momentum distribution changes, and what you're left off at the end is the rapidity distribution, which is unchanged from the beginning. So the way we do this in the lab is we have a 2D optical lattice, which gives us a bundle of tubes. And it's a blue detune, so the atoms are pretty free to move in the tubes axially. But we cap that off with this other cross-dipole trap, which is red detune, which confines them in the axial direction. Gives us the ability to independently change the trapping in the axial direction and in the tightly trapping tube direction. It's 1D gas because we start off with a Bose-Einstein condensate, and we turn on the trap. The atoms are all in the transverse ground states of these tubes. And we make the lattice deep enough that the tunneling rate from one tube to the next during the experiment is negligible. So it's essentially a quasi 1D system. And then we can either measure rapidities or show dynamical fermitization by first turning off the axial trapping and letting the atoms move in the way that I just described. And they evolve for some time. And if that time is long enough, what you end up is with a rapidity distribution, which you then do a time of flight on, which you're measuring the momentum distribution, but the momentum distribution is the rapidity distribution. And if you stop, if TeV is a little less, then whenever you do the measurement, it's just measuring the evolving momentum distribution. So to make it clear, what's a momentum measurement and what's a rapidity measurement? If we want to measure momentum, then this is just looking at 4 tubes sort of edge on. What we do is we rapidly shut off the lattice and the atoms expand perpendicular to the tubes, and then their interaction energies become much smaller in 1D. So all the evolution that would otherwise happen in the axial direction stops, and then a time of flight just tells you what the momentum distribution is at the time that you turn off the 2D lattice. So what that looks like is here, this is an example where we're starting off and just doing momentum distribution with no evolution time in the lattice, and it looks like this. And just to be clear, what that's saying is that because the atoms have flown apart dramatically, right? The initial size of the cloud is only about 20 or 30 microns in this direction, not that large. So they've really expanded a lot transversely, but there's not really no information in that. So what we do is we integrate in this direction, and what we see in this direction is then the 1D distribution. But if you do the same exact measurement with the same exact time of flight, after first allowing the atoms to expand for some time in the 1D trap, then you see the momentum distribution has obviously changed between here and here. And that is the process of dynamical fermitization. So this is what it looks like as a series of times. So this, the purple is the 0 time that you just saw. The red is the 15 milliseconds that you, or that color, whatever that is, brownish red, is the 15 millisecond time. And you see it's pretty much asymptoted to a final distribution, which is unchanging, and it goes through the stages of dynamical fermitization. So what you have in the end is the rapidity distribution that you had initially. And this is the theory, taking into account all the details of the experiment without any free parameters, and you see it's pretty good. In fact, if you, and the fact that this works as well sort of validates these rapidity measurements at all the other conditions that we measure rapidities. Just because, so I'm not really hiding anything by not showing the two things next to each other. If you just take all those curves and compare them 1-to-1, theory and experiment, see the theory is the dashed line. It's a little off in the initial condition because the temperature is not quite 0, but then after some time, it really is just exactly what you'd expect for a time serial gas, for a high gamma gas. Okay, so that's sort of an equilibrium experiment measurement of the rapidity distribution. The next thing that we did in characterizing the system is we followed up on this proposal from 2005, which is that you quench one trap into another trap. And then what was predicted is that you start off with some momentum distribution. It evolves. The initial evolution is really just dynamical fermitization. And then it continues to evolve, and it ends up, and it gets to the turning point of the shallower trap, giving you another peaked up Bose-like momentum distribution, and then it would just repeat itself over there. So we did that experiment, but we did it by first quenching for technical reasons from a shallow trap to a deep trap, but obviously it's the same thing. So what you see is this: the theory is red, the experiment is blue, and the theory is for the Tongue-Trudeau gas, and the experiment is for some finite coupling, which is between gamma of 8 and 2, right? 1 is right in the middle of it. Very high gamma would be the Tongue-Trudeau gas. So you see there's some differences in the period, the breathing things, some of the amplitudes of it. But if you rescale, look at comparable points over there, then you see that the distributions in both the theory and experiment go from Bose to Fermi to Bose to Fermi to Bose, et cetera. It just repeats. And actually this calculation of that with momentum distributions is beyond what theory can do at this point. Right, so we get qualitatively the same result as TG, but it's not a quantitative measure of what's happening. As you can see here, it's not great agreement. It's not measuring the same thing, which brings us to hydrodynamics, generalized hydrodynamics. So generalized hydrodynamics is just a hydrodynamic approach to studying the nearly integrable system, in this case the 1D Bose gas, where the sort of wrinkle on regular hydrodynamics is that there's a rapidity distribution within every cell. So you have an equation associated with each rapidity. And then through it, a lot of the magic happens in this quasi-particle group velocity, which you can get for each equation if you just assume that you've satisfied the local generalized Gibbs ensemble within a given cell. So that was first proposed in 2016. The first related experiment was done in Isabelle Buchel's group with a relatively high temperature, near the quantum degeneracy temperature in the weak coupling limit with a small quench, and then looking at the spatial distribution. And you see that you can only really match it if you include, you can't do it with regular hydrodynamics. You have to include the generalized hydrodynamics, which takes account of the rapidities. So we looked at this equation and we said, okay, there's really two essential assumptions for using the hydrodynamic approach. One is that you can use a continuum distribution of this gas, and the other is that you are locally equilibrated to the generalized Gibbs ensemble. So to test it, what we did is we start off with something which is near zero temperature, and in the opposite limit for this, strong and intermediate coupling. And we do as large a quench as we can, and then we measure the rapidity distribution as a function of time. So when you do that, this is what happens. So here we're doing a 100 times quench. So you go from a shallow trap to something which is 100 times deeper trap. So the atoms then collapse in on themselves. And these are a measurement of the rapidity distribution as a function of time. Starts off very cold, very low spread and rapidity distribution. It comes in and gets to some largest rapidity distribution. Then it comes back to this same point and it repeats because it's all integrable, even though there's a lot of interactions. And then we can do this and model an experiment and look at the theoretical calculation for GHD, and it's this. Just because it's so much fun, I go back there. That's the experiment, and that's the theory. Okay, so works pretty well. And this is in a situation where the average number of tubes per 1D gas is, the average number of atoms per 1D gas is like 11 particles, which, so it's maybe a little surprising that a continuum approximation works, but I think, the point is that the atomic wave functions are pretty spread out. Anyway, it works there. I mean, there's some details that get averaged out because we're averaging the result of a bunch of twos, but this includes everything, and it works when it includes everything. So the continuum approximation works even down to pretty small ensembles of atoms. We've also can look at the way the energy evolves. So you can measure the energy by adding up the sum of the rapidity squared across the distribution, and you see you get this oscillation in accord with what the theory says it would do. We can also measure the kinetic energy, and that's just taking the momentum distribution. Yeah.
it's a static system, right? You do a quench and then afterwards energy should be conserved. How can the energy oscillate?
No, it's the rapidity energy. So what's happening is it's an exchange between the rapidity energy, total rapidity energy, and the trap.
Okay, but
Trap potential energy. So that's true over here. Here, it's only kinetic energy. So the difference between this and this is the interaction energy. That's the third point of interaction energy, which is clearly much higher at the point where the things are maximally compressed.
Yeah.
And just to give a flavor for what that is, we're starting off with something which is 17 microns long for the length of the tube, and this compression leaves them off at the minimum size at only a half a micron. So really dramatically changing the gamma from about 9 to about 0.2. Okay, so it's changed by a lot. So if you think about the many-body wave functions looking like, it's really changing from what it looks like at the beginning of my cartoon picture, where the single particles are avoiding each other, to things that are nearly overlapped with each other, but GHD keeps track of the whole thing. So, we try to change things fast enough so you can look at this as testing the other part of GGE, but of the GHD, the fact that it still continues to work even when you've tried to do changes pretty rapidly. And then just, you see not much was happening in essentially those first two cycles, but if you look farther in, then there starts to be extra complications that happen as these particles are moving, and that's also captured by this theory. So it's a quantum, heavily entangled quantum system going through 6 cycles, and we still get good qualitative agreement, even for some pretty funky shaped curves at the later time. Okay, so GHD works super well. So because we're reasonable experimentalists, we say, okay, the next thing we're going to do is we're going to try to make it not work. What do we do to make it so that GHD doesn't work? So before I describe that, I'm going to have this slide, which at first glance might seem like it's totally out of the blue, because it is concerned with relativistic heavy ion collisions. And in relativistic heavy ion collisions, where they're trying to form and study a quark-gluon plasma, what they find when they look at the result is that they can take what they measure at the end of the collision and work back to the initial collision. And they find that they can work back theoretically using hydrodynamics to a time that's really close to when the collision first occurred. And it's at a time which is so close to that time that it's clear that each of those cells in their hydrodynamic theory doesn't have enough time to fully thermalize. They're not locally thermalized, yet the theory works back to a very early time. And they're the ones who came up with this, to describe this process with this abomination of a term, hydrodynamization. We've used it because it exists there in the literature and it ties in with them pretty well. So it's basically on this thing where these are compressed, space compressed, contracted heavy nuclei, and they collide together, and then you form this quark-gluon plasma. The hydrodynamics works from about the point where it's overlap with each other. It's less than 1 femtometer per C when it happens. Okay, so that's where the term hydrodynamization is coming. By the end, I get back to relativistic heavy ion collisions. For now, come back to the 1D gases. What we do is we do a Bragg pulse quench, which changes the wave function very quickly. So we just put on a short pulse, and then clearly right after the short pulse, the GGE isn't satisfied, right? And it's actually, you can't do any sort of exact theory in this region except for in the infinite coupling limit. And what you see then, if you measure the rapidity distribution after that pulse, is this is the rapidity distribution. It's center one with some Bragg peaks on the side. And this is a time which is short compared to what will be the following oscillation in the trap. So, with 0.5 milliseconds, it's short enough for that you don't even see these side peaks starting to slow down, which they will eventually do. And you see the notable thing is that because therefore the trap looks like it's effectively flat, not flat, but unchanging for the atoms. The atoms aren't moving in it. Then this rapidity distribution is conserved over this time. Okay, so this is a whole bunch of them. They're all just totally overlapped with each other. So, okay. So early on, rapidities don't change because they are conserved under those conditions. But the system does evolve. And if you want to think about the evolution of the system, it's because each rapidity evolves according to its rapidity energy, kinetic energy associated with that rapidity. And that's a different phase factor for each of these terms. So if you look at the other measurable that we easily have in the system, which is the particle momentum, it's going to depend upon the rapidities, and it's going to depend in a complicated way, right? Because each particle, each quasi-particle, which gives you the rapidities, involves all the actual particles. So the mapping between them is highly non-trivial. But you can sort of see something generally about it is that we know what the time scale for the evolution of the phases of the rapidities, and that's going to be the time scale for the evolution of the momentum amplitudes, right? Because a change in the rapidity phase, how those are going to get together to tell you what's going to happen with the rapidity, with the momentum, is complicated, but it's going to change on the same time scale. Okay, so let's just think about what those time scales are. It's actually two energy scales in the problem. There's the size of the difference between the zero peak, the initial one, and then the Bragg side peaks. That's h omega d, omega ht. That's the characteristic hydrodynamization frequency. And over this time, as that changing, what I'll show is that the momentum is redistributed among momentum modes in a very complicated way, totally non-locally within the momentum space. The other time scale is this delta theta, and that tells you something about the dephasing of the hydrodynamization, right? Because it's not just one frequency, but it's a range of frequencies, and you add them up together when you're looking at any given momentum group, and it's going to take what would otherwise be a pure oscillation and make it damp out. Right, so this is just one time scale. This TDP depends upon what the particular observable you're looking at is. We're looking at momentum, but any observable you looked at would vary for how this spread in energy is going to affect going to quantitatively affect the evolution, but it will scale in as this delta theta. And then the other time scale is local prethermalization. That's the approach to the local generalized Gibbs ensemble. And that also is going to scale as this width, generally with a different coefficient, and also in a way which depends upon the particular observable that you're looking at. Now, what you see is that for this sort of process, you're not getting changes of momentum of amplitudes that go from one side of the distribution to the other. It's more like a flow of momentum from one group to another over there. So you see, these two processes both depend on the same energy feature, but they depend in different ways, right? Because this has to do with the phasing of these fast oscillations. This has to do with something else, and typically that something else has a semi-classical picture that you can have for it. Okay, so now this is the momentum distribution where something does happen for the same system. So momentum distribution, and you see a few things. First, I've gone a little bit farther than that half a millisecond, because if you go farther, then you see that you do start to have these side peaks slow down. Okay, but everything we're going to talk about is going to be focused on, the local prethermalization, hydrodynamization all happens in less than a half a millisecond, where those haven't changed. But you see the peak drops in both of these things, and the width and associated with grows. And that's local prethermalization. That's the sort of obvious feature that you have over here. And you can see, it is this sort of change as momentum amplitude flows from one group to nearby groups. But before that, that's when hydrodynamization happens. And it's a little hard to see on this picture. So we look at it in a different way, which is that we take this distribution and break it up into different momentum widths. And in each momentum width, we count up the total energy that is in that momentum group. So, and plotting up on a log scale, it looks like this. So this is the momentum group right in the middle, which has not a lot of energy, a lot of particles, but not a lot of energy because it's near zero. And then the top of this other peak are these two groups over there, which has a lot more of the total energy because the momentum is larger. And this puts all the data that we have together. I'm just going to break it up on a linear scale to make it a little easier to see each group, what happens in each of these regimes. Right, so this one is near the peak over there. These two things are near the middle, and these two are near the center peak. So for the ones that are near the peak, you see this oscillation, and that is the omega HD that you can calculate for this thing. That's the oscillation period of hydrodynamization. And then you see it also damps out. And similarly, this is an out of phase oscillation. It's also the hydrodynamization frequency, and it damps out. And then this extremely rapid change for these middle things, where you're starting to get amplitude which you didn't have at all. You had very little to begin with, and you get a lot more. That's happening on a super fast time scale, because that's where presumably those momentum groups, which are in the middle here, draw from here and here. They're all contributing, so you're getting a maximal sort of dephasing of the different groups. So it dephases extremely rapidly. So this is a surprisingly short time for the evolution of these momentum components, and that is of these momentum components, and that's indicative of hydrodynamization. So that's the experimental kinetic energy. If you do the same thing with the same sort of energy, but in the hardcore limit, this gamma is like 3.5, I think, for this data, hardcore gamma infinity, you see it's qualitatively the same, especially with regard to hydrodynamization, with these oscillations and the damping. And the details are not the same because the mapping of quasi-particles to particles, vice versa, are different for these situations, but they qualitatively remain very similar. And just to be clear, if we look at the experimental rapidities and look at the same thing, they are not changing at all over this time. They're just constant because the rapidities are conserved on this time scale, but the momentum is not, because it's evolving because of these difference in rapidity phase. And then another way to look at this, we can only look at this in the theory, is that what happens is you give the Bragg pulse and you write in a grading at lambda over 2 of density, right after that pulse. And then hydrodynamization consists of oscillations in that density, and hydrodynamization damping consists of the damping out of those oscillations. Okay, so that's hydrodynamization dephasing. You can also look at local prethermalization in the system, process of approaching the local generalized Gibbs ensemble. There's a semi-classical picture which you shouldn't take too seriously, but it gives you sort of a flavor of what is going on over here generally, and it sets a limit on the time scale, so that the Bragg peaks move and they move some distance, which is characteristic of the momentum that you're considering, some characteristic distance associated with that wavelength, then you get some local prethermalization time for that wavelength. So what we actually do is we measure more carefully the change of the momentum occupation near the half maximum points over here. So here, look at the near the half maximum points, and then at a different spread of the energy with the side peaks, we look at the spread how that same feature changes. And as long as you're looking at the same feature, you'll see that the time scale associated with changes in that feature scale with this width. So that's what this shows, is that the change in the feature size just scales with the width, which is just what our general model of local prethermalization would say. So that's the experiment. This is the theory, says that, well, the actual rate of local prethermalization does depend upon the G1D term in the Lee-Linear model. The other thing I just note about this is that when you look at, as we'll see a little bit later, you look at the dephasing of hydrodynamization in the theory, there's a little bit of overlap of that with the time of local prethermalization. So, they seem like they're almost maybe related to the same thing. But in the experiment, there's this extra factor of 2.5. So there's a really good separation of timescale between this phenomena, which is this flow of momentum nearby associated with local prethermalization, and all the hydrodynamization stuff, which is just much faster. So we've did a lot of theory, or Yicheng Zhang did a lot of theory. We helped with where what we did is instead of trying to model the experiment, we just set up the theory with a homogeneous system and started off with a given rapidity distribution as opposed to providing pulses, which simplifies the theory to a large degree. And what we found when we look at it in detail, the presence of the pulse is not important for the evolution. The fact that it's homogeneous or inhomogeneous is not important. So what you see is a bunch of features for these curves. So what these curves correspond to is, some conditions, and then say for this one at a given width of the side peak, we change the width of the hydrodynamization energy. And then at that same hydrodynamization, we change the width of the side peak. And then you see a bunch of things that you can extract from this. One is that hydrodynamization scales as 1 over the momentum squared. Those oscillations scale as that. The damping only depends upon the width of the side peaks, and that's illustrated by the fact that the damping of the hydrodynamization is always within these gray bars. These are different axes over here. Take my word for it. And then local prethermalization depends on P. You can sort of see the local prethermalization of the lowest energy, the highest amplitude elements over here, and it becomes pretty slow over there. And then it gets faster and faster as you move to what are higher amplitude modes. I mean, here we're looking at not the energy, but the amplitude in a given momentum mode. And they change with P, and then the longest prethermalization times are clearly longer than any sort of hydrodynamization damping time like this. And those are all features of this thing. Okay, maybe that's more than you needed to know, but I'll go on and tell you other things that you probably do need to know to really fully understand this. So what we did is we set up a situation where there are only 2 peaks. That's a quantum Newton's cradle pulse where you give one Bragg pulse, wait a little time, and give another Bragg pulse. And what that does for the momentum distribution is it mostly depletes the zero momentum group. And so this is the experiment. This is theory, where you see theory, we have access here to the rapidity distribution. We take away most of the rapidity distribution over here. Here, this time we look at the momentum. You can also get rid of most of the momentum. So you specifically make it so there's only 2 peaks. Now you see when there's only 2 peaks, the spread in energy becomes much smaller because this peak has the same energy as that peak. So if you ignore the side peaks for a second and just look at those peaks, then you say, okay, there shouldn't be any hydrodynamization at all because that hydrodynamization timescale is absent. And that's in fact what you see in the experiment and the theory. If you look at all the momentum groups in over here, they after that second pulse happens over here, the things come back to something more like where they were at the beginning, and then they don't have this hydrodynamization over that time. So the hydrodynamization depends upon this 3-peak structure. If you do something where you set it up in the theory and just take away these extra higher Bragg peaks completely, then you see there's no evolution at all over here. It's totally flat. Okay, so just a couple more things I want to tell you. One is this spatial picture of hydrodynamization, where you're starting off with some spatial distribution, and then you give this Bragg pulse, and it's like suddenly putting in 2 groups, or having an amplitude in part of a wave function which is going this way and part of a wave function going this way right from the beginning. So after that Bragg pulse, it's like suddenly you have a collision everywhere in the gas all at once, right? Which really has to be the way it is, because if they came in and you had like a cloud here and a cloud here, and they combined, then they would constantly have a collision at the interface, and they would hydrodynamize and locally prethermalize faster than the things actually get over take to overlap with each other, right? So we get this immediate precision, immediate collision, and in that time, in this pretty short time, we get this redistribution of momentum in all these different groups. And I note, I haven't shown you over there, but I'll tell you that that hydrodynamization can be faster than the time it takes for a particle to move between the average interparticle separation, because basically it doesn't have to do with that. It has to do with this quantum many-body wave function, right? As opposed to local prethermalization, which can't be faster than that, than that time. Okay, so then once the hydrodynamization runs its course and dephases, that's the time that you can first start to use generalized hydrodynamics, right? Because before that, you could use generalized hydrodynamics if you ignored the fact that there were these density oscillations. But if you want to actually model what's happening in the system, you got to wait for the density oscillations to smooth out before you can apply generalized hydrodynamics. And after that time, because the rapidity distribution is basically conserved over the time of the course of local prethermalization, it's clear that GHD applies exactly, even independent of local prethermalization happening, right? If you think about what the measurement is like, you can't even really tell the difference between waiting a longer time and measuring the local prethermalization or not waiting, measuring the rapidity distribution or not. It's going to be the same result. So we have GHD absolutely works before local prethermalization is complete and after hydrodynamization dephasing is complete. So now we get back to relativistic heavy ion collisions. It's 18 orders of magnitude higher in energy, and you have this this collision. So here, the nuclei overlap in a very short time. That short time is on this scale, it's like 0.1 femtometers per second, femtometers per C. It depends upon exactly whether you're talking about RIC or the LHC, but it's a very short time where these things are overlapped. So at that time, right from the beginning, so that time of getting an overlap is sort of like what the Bragg pulse is. And then there must be some way to describe all the interactions among all the particles over there in some kind of quasi-particle picture, which we can't do, but to say there is some quasi-particle picture that will incorporate all the interactions in the quasi-particles as opposed to in real particles in this incipient quark-gluon plasma at the beginning. And so, having said, and also you say, what is that? There's a quasi-particle picture. There would be therefore some hydrodynamization timescale. It's reasonable to assume that when these things come over on top of each other, you started to populate the zero momentum peak of the whole thing, the at-rest quark-gluon plasma, and you still have some of these high rapidity groups on the side. So it really does look just like the situation that we were talking about over there. Now it's not just a single bunch of atoms or bunch of atoms with only momentum. You've got all sorts of different modes of the quark-gluon plasma you're considering. Now, that quasi-particle picture, since this is a totally non-integrable system, is not good for very long. Those quasi-particles, that whatever you had, are going to decay rapidly. It's just that the hydrodynamization is the fastest possible timescale that you have. So the decay of those quasi-particles are going to be slower anyway than the hydrodynamization timescale. And so that's the first thing. The second thing is that, and what makes this sort of so satisfying at some level, is that the hydrodynamization dephasing time you can get by, get what the width is of the rapidity distribution from just looking at the space contracted delta x over there and use the uncertainty principle to get some delta rapidity or the momentum of the quasi-particles. And that answer, because it's all relativistic, turns out to be independent of the quasi-particle mass, which is good because we can set some limits, but we don't really know what the quasi-particle mass is. But whatever the quasi-particle mass is, we can get a an estimate of what this hydrodynamization dephasing time is. And it turns out that those hydrodynamization dephasing times are either comparable to or a little bit shorter than the hydrodynamization time in those experiments, which is then the point at which hydrodynamics starts to work to describe those systems. So, it couldn't be before then, and there's a reasonable expectation that once hydrodynamization is complete, then that's when a hydrodynamic picture could start to work. So that is, during the hydrodynamization time, you have a redistribution among distant modes of this system. It's complete by the time of hydrodynamization dephasing, and then here, not local prethermalization, but local thermalization would continue, but it doesn't have to be completely finished before hydrodynamics would work well, as long as all the stuff associated with hydrodynamization is completed. So what I've told you is that we can use these 1D gases to measure rapidities and then to test generalized hydrodynamics. Since it doesn't have to be an integral system, it can be a nearly integral system. It's a pretty large space, and the idea is to try to get insights into more generic dynamics. So along those lines, we've elucidated this hydrodynamization, which is always going to happen whenever there's a high energy quench, and a spread in energy in any interacting quantum systems, kind of independent of the details of that interacting quantum systems. And we've also observed this local prethermalization and studied how it goes. So now in the lab, we're working on another way to sort of specifically take these gases and make them less integrable in order to see if we can use generalized hydrodynamics and adapt it to a progressively less integral, not nearly integrable system. And that's the work in progress. But for now, that's what I have to say. Thanks for your attention.
Thanks a lot. More questions?
Yeah. Okay, let's start.
I'm still trying to get my head around the idea of hydrodynamization. I mean, I understand in the high energy part, it's basically you can start with the observation. You say, okay, well, hydrodynamics seems to become a valid description at this point.
Right.
But now you're saying, okay, why is hydrodynamization always the first thing that happens?
Right. Okay. And that's because, just come back to here. Because if you look at this picture of some rapidity distribution, then actually, I can just do it here. All the evolution is contained in the phase evolution of the relative rapidity things, of the relative rapidity distribution. And the highest energy available for a differential phase of in this system is that rapidity energy. Is that hydrodynamization energy. That's the highest one. There's nothing else that can possibly be faster than that.
But I need the dephasing of the hydrodynamic oscillations for the picture to become valid, right? So I kind of need the width of the peak of 2h bar k. If there would be a delta peak, I would just have an oscillation.
That's exactly the way it would work. If you just had a delta peak, you would have hydrodynamization oscillations, which would go on for a long time.
Okay.
Right. So it's the hydrodynamization is sort of the dynamical thing that happens, which we can see directly in the experiment. But if you want to get to the point where you might be able to apply hydrodynamics, you've got to wait for the dephasing, and therefore it depends upon the width of this thing.
So right. Thanks. Yeah.
Which could be extremely narrow, and then the thing would go on for a very long time.
I'm also trying to understand here. So again, the hydrodynamization time is that at which essentially you have like random phases, and then you can start thinking about just computing probabilities of events like scattering or decay using Fermi golden rule or these kind of things, and then this has to be the first time scale, and that the time scales that come from the semi-classical rates are
so
much larger.
Just to start off before the local prethermalization, right? The evolution associated, I mean, first, all the evolution is contained here, right? Or the only thing which you don't see in the in this setup over there is what the initial relative phases of the different rapidity distribution, or different rapidity elements are. Right, so exactly what happens at the beginning does depend upon what the initial relative phases of those things. In fact, we can set up a situation where the initial relative phases is such that it doesn't evolve, that it's already ends up in the steady state final state. It's just that so it's entirely contained in this picture. Or so this idea that you have to look at some collision or something else that happens, you don't need it. It's all right here. It's all because you have this thing. These are essentially like eigenstates of the system, these unchanging rapidities.
Just to follow up exactly what you said. So there are phases in the initial state which are not represented here.
Right.
However, you say if I wait the time sufficiently large, whatever those phases were, the dephasing will randomize them.
It'll randomize the phases and you will get to what is, if you haven't changed the rapidity distribution, you'll get to the generalized Gibbs ensemble.
Okay.
In the end, it'll be the local generalized Gibbs ensemble which it would go to. So depending upon the initial phases, you could start off with something which is already close to the local generalized Gibbs ensemble.
And these will be random phases.
It's actually not random phases. In order to do that, you need to start off in superpositions of where your states are equally one side and the other side. So the way we set this up for doing this, we keep the separation between each momentum group and each rapidity group and the associated plus and minus sideband sort of moving with the center. If instead of doing that, you start off in the center and just set up states which come from the center. Sorry, instead of here, we have some distribution and say if this goes with this, that's the way we set it up. That's more like what happens in the experiment. But if you set up to begin with where you have distributions which are here, and then when you come to there, it's here and here. That is, if you set it up so it's symmetrically, then you're actually already close to the generalized Gibbs ensemble at the end.
So if I can comment, I think
I mean, it might end up being random in the end.
After equilibration,
Yeah.
and then,
Yeah.
Yes.
I mean, certainly
Yes.
nothing else is nothing else. There's no memory of the initial condition other than the fact that the rapidities aren't changing.
And
The phases have no memory.
And if I may, another question about the AV ion collision. So I assume they have a model for parton distribution functions for within the nuclei.
Yeah.
And the assumption is that the partons inside are essentially free at these energies, and then you can apply all this.
Yeah, I mean, it's a
Okay.
strongly interacting gas in that situation over
Yeah.
there. But yeah, I mean, whether at the end, maybe Marcos knows better, whether at the end there's a, yeah, right. But the fact that it's strongly interacting doesn't mean, whether the parton numbers and, the mode occupation of the different partons is entirely fixed by the end of hydrodynamization is not totally clear. It's just saying that it's evolved to such a degree that you can still describe the whole thing with hydrodynamics, but it doesn't mean that you're necessarily in the final state of those systems, right? In the final distribution.
You say we're strongly interact because I would have said that this end,
very viscous.
it's very viscous
Yeah.
hydrodynamics.
There are some dualities, some people have used that to solve that.
Okay.
The viscosity.
Yeah,
I see.
and there's been a lot of work, obviously, in the high energy community trying to understand this, trying to set up models because it's hard to exactly calculate what's going on in that collision. And, there's some echo, if you look at that work, of the kind of things that happen from this perspective. I just say that this perspective on it seems to me to be super clear, and generic. It doesn't give you the answer because we don't know the details of the system really, which they try to incorporate in those models. But it tells you sort of physically why it should work, why the core physical process happens, which is that you have this thing which has to do with having a many-body wave function and again, having that many-body wave function where you can understand that it behaves in this way is just made super clear by the fact that we start off with an integrable system where a lot of other complications go away. But then once you realize that that's the way that it works, you see that the fact of integrability is not important in understanding short-time behavior. Yeah.
But now you took me over. I mean, the story here is that the short-time
behavior is the beating and then the dephasing of the rapidities.
Right.
And that's all there is to it, the phases of the rapidities, because they're conserved quantities.
Right.
But when I think of the 3D heavy ion collision where it's not nearly integrable,
Right.
So what is the equivalent of the rapidities?
So the point is that we don't know what the quasi-particles are. We don't really know what the rapidity distribution is in any sort of detail at the point of the collision. But if you look at you just look at an instant of time, there must be some way to include all the interactions to make it so you have these more free particles, which include the interactions, which are the quasi-particles. So most of the interactions are folded into the definition of what the quasi-particles are. Now, those quasi-particles are going to decay.
Yeah.
Right. They're going to decay because you're going to have collisions among the different elements, which are totally not integrable, and you're going to have different quasi-particles at a later point.
Yeah.
But the point is that decay process is going to still be slower than hydrodynamization, which is the highest possible energy scale.
So,
right now,
do we know that? I mean, they
know that
damped, right?
But there would be a possibility that the hydrodynamization damping would be a lot slower. Right. So it's true. If you had something where the width of those things was very small, then you might have to worry about the quasi-particles decaying before the hydrodynamization damping has occurred. So, I mean, it is possible. It just seems sort of unphysical in some way. I'm not impossible unphysical, just
okay.
Right. They are. It's hard to see how they would end up being so narrow. I mean, in fact, we have a lower limit as to how wide they have to be. I mean, they can't be. There's a minimum possible width given by the uncertainty principle and the width of the wave function. And that's the only thing that we're doing for putting in there. So we just say, okay, it's at least that wide. And if it's that wide, it already explains the time. Right. So the hydrodynamization time is faster than this, but the hydrodynamization damping time is the time that we're approximating. We're using this delta X uncertainty principle to determine what the hydrodynamization damping time is, or what I guess it's an upper limit to the time. I'm trying to. It's the width delta omega has to be at least some big, so the time has to be at least some amount of small. Right, so it can't be smaller than that.
Okay.
So we set that lower limit, and that's about the time where they say that it works. And the amazing thing is that the parameters in these high energy experiments are pretty different, right? But this works for both of those different situations. So, maybe it seems like it's the basic physics that's going on there.
Some more questions? Okay, if not, we can thank David again.